Welcome back. In today's video, we're going to show you how to size a braking resistor when you're trying to stop an inertia load. In other videos, we might show how to size a braking resistor for an overhauling load, and in a different one maybe for power quality. But that's not what we're doing today. In today's video, it's just about stopping the inertia load. To make sure that everyone understood, I came out with an outline that we were going to follow, but then the video was way too long. And so I started trimming some steps out of it that we were going to talk about. And then I tried to make the video and it was still way too long. So then I trimmed it some more. And then because in my head I wanted to talk about all this stuff, I still was making it too long. So what I'm going to try to do is go through these 8 steps and not talk that much. I'm going to try to just trust that you can follow me along without me having to say much. Luckily, the way I did this video, all the data is on the screen, and if you get lost, you can pause the video and pretty easily figure out what I might have missed in the video, right? It should be pretty easy. And if you have a problem, you can always ask questions in the comment section. To help make things easy, I came up with a simple system that we're going to use as our system we're going to stop. So I'm going to label all the items so that everyone can understand what we're going to be talking about. So this is a very simple system. We have a motor, we have a load, and 2 motor pulleys between them. You can see that the motor pulleys are different size, and this makes a belt ratio on this particular system of 4:1. This is a very important piece of information. The reason it's important is because when you have a spinning mass like this load, it's storing energy, and when you try to stop it, that energy is going to go through the pulley system, back to the motor, and then from the motor to the drive, and then the drive's going to freak out because it has nowhere to put that energy that it's just received from that spinning load. And so the braking resistor is added to a VFD so that it can melt away the energy into the air, okay? Now, the amount of energy that's stored in a load has to do with the amount of inertia it has and how fast it's spinning. So what we want to do in order to make things easy on ourselves, we want to find what the inertia is from the point of the motor. Okay? So instead of having a whole bunch of inertias all over the place, we just want a single inertia, and we want to know what it looks like to the motor. Here is your equation for doing that. Basically what you're doing is summing up all of the inertias, except you're going to notice that there's a division in here. If you look right there, that division happens because of the belt ratio. Because the belt ratio here is a 4:1, it's a division. What that means is the motor has to turn 4 times for every 1 time of the load. So basically, this is great because the inertia of the load goes down by the squared of the ratio. That's awesome. However, if the belt ratio was an increaser, in other words, it was a 1:4, where the motor spins 1 time, and then the load spins 4 times, then this division symbol here would need to be replaced with a multiplication symbol. Remember what I just said? The amount of energy stored in the load is based on the speed and the density. And because it's going to be going so much quicker, it's going to have a lot more energy stored there. But in most cases, it's always a reduction, and it's going to be a division like this. So here are the inertias for today's example. You can see that the pulleys, I just said they were 0 inertia, right? And I have the inertias on this screen currently listed in 2 ways: pound-foot squareds and kilogram-meter squareds, okay? All of the math that we're going to be using today is based on kilogram meter squared. So if you have any kind of units that are not kilogram meter squared, you will have to first convert those to kilogram meter squared. Okay? Now, if we look at our equation here, because our pulleys are 0, those are just going to be deleted. And it's going to simplify into this, okay? And as we just plug and chug stuff into it, you're going to see that our inertia isn't that big. It's actually pretty small. it's 0.025 kilogram meter squared. Okay? From this point forward, I've split the screen from right and left. On the right side is our applications requirements, and on the left side will be what we're trying to solve, like the math that we're doing currently for the different parts. Okay? So the reason I did this was so that you didn't have to go back and forth in the video to find what the requirements are. You can just look left and right and see the way they look. Okay? So our requirements are, we have an inertial load of 0.025 kilogram meter squared that we need to stop. We're going to stop it every 30 seconds. Our deceleration time is 5 seconds. So that's how fast we want to stop it. And our speed that our motor is going to be running at is 1,475 RPM. Now this is the speed of the motor, not the load. Everything we're going to do in here is always from the point of the motor. Okay? Now, you'll notice that I added stop speed and delta speed. I only put it on the screen to make the point that you can use this same procedure that we're going to do today for systems that are just cycling between a high and low speed over and over again. Okay? The other pieces of information we're going to need is the motor rated torque, and we're going to need two things from the drive. The minimum resistance that the braking chopper supports. In this case, this drive supports 25 ohms or more for the braking resistor. And we need to know what the DC bus voltage turn-on point is. This drive here is a 240 volt drive, which means that the DC bus can go as high as 390 volts DC before it starts to try to send power to the braking resistor. Okay? If you had a 400 volt drive or 460 volt drive, then the DC bus would start sending power to the braking resistor probably at 790 or 780 volts. These two pieces of information you can find in any drive manual. So the first thing we need to do is verify that the motor can actually stop the load in the time that we want. Now, a lot of people will just assume, hey, someone sized the drive and the motor, therefore it should. From experience, a lot of people will size things correctly for the application's needs, except they ignore the e-stop condition. So a lot of times the e-stop condition will be a lot quicker than the normal application. On the left side, you'll see this equation. And what this equation is telling us is what is the fastest or the shortest deceleration time that this motor will support if we're just using the normal rating of the motor. If we're using peak, of course, we can be a little quicker. I like to tell people to just use the normal rating of the motor because then you have a little bit of overhead in case you messed up on sizing somewhere. As we can see here, this motor can stop the load in 1.5 seconds. And according to our application, we only need to stop in 5 seconds. Therefore, this motor can easily do what we need it to do. The next thing we need to find out is how much torque is needed to decelerate at the 5 seconds. And that's what this equation here is for. Okay? And you can see that it only requires 0.8 newton meters, which is less than the rating of the motor. On the left side of here, this equation finds the peak power. Now, the peak power is the amount of power that's going to flow through the braking transistor right when the drive starts sending power from the drive to the braking resistor. The reason this is important is because, first off, our next equations are going to use it, and you can also use it to double check that the drive can support this kilowatts. Okay? So now we're going to find the average power. Okay? We just found the peak power of 0.1235 kilowatts, but there's a problem. That is assuming that it's a constant velocity application. Basically, it's an overhauling application. What we actually want to know is for a stopping application. And a lot of people kind of mess this up. They end up using the previous kilowatts for sizing their braking resistor. It's going to make their braking resistor oversized. Okay? Now, the previous kilowatts is great for overhauling conditions, but it's not so great for stopping conditions. And that's because as you slow the load down, the amount of energy coming from the load also decreases. And the final equation is the cycle power. It's basically the average, but for cycles that are happening over and over and over again. Now, I see people use this equation all the time and get burned also because they have long dwells. Okay, so let's say I have a really quick deceleration, a really large load, and then I dwell for like 3 days, right? Well, if they use that extremely long dwell time, of course, the average cycle power is going to look like nothing. So then they're going to undersize their resistor, okay? So you don't want to do that. So where this is important is if you have a system that's going start, stop, start, stop, start, stop, start, stop, you know, it's just like part of the normal behavior, then the cycle power here is great for sizing your braking resistor. The next thing we need to find is the maximum resistance that will work for the application. What this equation does for us is it tells us what the maximum resistance can be. So in other words, for our example, we need our resistance to be less than 1,231 ohms, but we need it to be more than 25 ohms. So anything in that range will work for our system. The resistor also needs to be sized correctly for the wattage. Now you'll see in the bottom here, we found a peak power, an average power, and a cycle power. Now if you size it on peak power, well, your braking resistor is going to be oversized. It'll work, guaranteed. It's just going to be big, right? If you size on average power, you'll be good too. Except that if someone messed up with the inertia, right, and the values you were receiving are a little off, then it's not going to. So what I would recommend is you add a little bit, somewhere between average and peak. And the reason I suggest that is just to give yourself a little overhead. Cycle power, I usually don't recommend sizing your resistor for this condition. The only time you would use this is if your system is cycling up and down, up and down, up and down constantly, right? And that the dwell times are short. If the dwell times are long, then your cycle power is going to be showing a very small value, and it's going to probably be not enough for your system, especially if your deceleration times for your e-stop or your emergency stops are quicker than your normal cycle deceleration stops. Thank you for watching. If you enjoyed the video or you found it useful, please subscribe or share it with somebody. And I'll see you next time.